If we have all of that oxidation reduction balancing half reaction sheet, I'm just going to do one sample problem at the bottom of the page. Actually, it starts on the bottom of the page and continues on the back side. This is what WebAssign is going to be based upon as well. So the top part gives you an example. I'm skipping all that. On the very bottom, it says number 1. Aluminum metal displaces iron 2-phosphate in a single displacement reaction. It asks us to write the skeleton equation. All that's referring to is we don't have to worry about balancing with coefficients necessarily. Aluminum metal. Iron 2-phosphate would be Fe3PO4 And if it's a single displacement reaction, the aluminum metal will replace the iron. So now iron is by itself, and then aluminum phosphates together. The goal of this question is going to be to figure out what was oxidized, what was reduced, and to write those types of equations. So I'm not going to even balance this right now because it's not important to me. You notice the last bullet point on this front side says assign oxidation numbers. Aluminum by itself has what for an oxidation number? 0. I mean, so does iron. Iron on this side is a +2. Aluminum on this side is a +3. Honestly, I'm going to ignore the phosphate. It's going to be a spectator ion. It's not going to matter. So on the back side of this worksheet, we should be able to write a reduction equation and an oxidation equation. So we have to remind ourselves of what does it mean to be reduced. To be reduced means you gain electrons. You look at the oxidation number. If the oxidation number gets reduced from start to finish, it gets smaller, it's the thing that was reduced. So was it the aluminum or the iron +2 that was reduced? Iron +2. And again, make sure it's the iron +2. We don't say iron because products don't actually change, or they don't get reduced or oxidized. Again, it could be written as +2 or 2+. Either way is fine. But if it's a reduction equation, it's going to gain electrons to become the iron 0. If you want to put the 0 down, you can. You don't have to necessarily. Then I balance my equation by getting the charges on the left and the right side equal. It must have been 2 electrons that were gained. Hopefully that rings a bell from Unit 1. Oxidation, well, that must be the aluminum. In an oxidation equation, you only have the thing oxidized on the left side of the arrow. Because on the right side of the arrow will be what has it become and however many electrons that it lost. In this particular problem, to balance it out, there must have been 3 electrons lost. If you're following along on that worksheet on the back side now, the third bullet point from the top says write a balanced equation so that the electrons lost equals the electrons gained. This is something that we kind of wrapped up redox with last unit, where notice how there's 2 electrons gained and 3 electrons lost. What we can do is multiply everything in this equation by 3 and everything in this equation by 2 to make it so it's 6 electrons gained and lost to balance that out. Then, if I write that net overall reaction, I can kind of add these 2 together after I do that. So my overall equation would be 3 of the Fe +2 plus 2 of the Al will make 3 of the Fe0 plus 2 of the Al plus 3. So what this equation is saying is that I had 2 aluminums reacting with 3 irons to make the 3 iron ions, to make the 3 irons and the 2 aluminum ions. How many electrons were transferred? It was 6. That's the number of electrons that were balanced out. Is there questions on this? And this was meant to be a quick review. This is what the WebAssign is. The WebAssign will probably take you about 5 minutes tonight. However, what I want to do now is move into why are we reviewing redox? Because we have to go over how electricity works. We're not talking about stuff that physics might cover with electricity. We're talking about chemical electricity. So how do we create that electric current to begin with in terms of things being reduced and things being oxidized? So we are going to now move into the notes part dealing with batteries, because this is where we have an application of redox chemistry. And as my title slide states, we're taking chemical energy and making it into electrical energy. The lab that we do next week, Monday, will be doing this very thing. Okay. Fair amount here on the first slide, so let me talk about it first off. A battery cell is referred to as a galvanic cell or a voltaic cell. So there's two terms used to talk about a battery cell in chemistry, galvanic or voltaic. And again, what we're doing, the first bullet point states, is we are going to create electricity through a redox reaction. I give you a fairly simple redox reaction for my second bullet point. Zinc plus copper ion makes zinc ion plus copper. What I state then is that the zinc is losing electrons to the copper, so the zinc must be oxidized. What we can do in a galvanic cell is we can connect the different metals through a wire, and that current of electrons that can flow from zinc to copper, that current of electrons is what electricity is. Electricity is just the flow of electrons from point A to point B. We can harness that flow of electrons in order to have electricity so we can have things do work. So why we have to go over redox before we go over battery cells is because battery cells are electrical energy. It's storing that electrical energy to be used for something. How do we create electrical energy? Something's oxidized. It's losing electrons to something else. It's being reduced. There's a flow of electrons that we can now use in order to power something. So I'll give you a minute to jot this down, and then my next slide, I'm going to show you a picture of a very simple galvanic cell. Again, the batteries that we make are not going to look like 9-volt batteries or AA batteries. We're going to be making batteries with beakers, and solutions, and metals, and stuff like that. Again, the very last point on this slide, that flow of electrons, because something is losing electrons and something is gaining electrons, that flow of electrons is the electricity. It's what we can use to power something. Okay, we are going to move on. Okay. Boy, this doesn't look like anything special, does it? A typical battery cell that we're going to make in a lab, and pictures of this are often used in the AP exam as well, because electrochemistry is always one of the free response questions. Again, I don't know all the multiple choice that's going to be on there, but I see the free response year after year. This topic is always on there. On the left-hand side, it might be hard to see, but they're showing copper metal. That's why it's kind of orangish brown. That would be in a copper solution. On the right-hand side, the silverish metal is zinc. So I'm basing it off that equation I showed you in the previous slide. That's zinc metal in a zinc solution. And then there is a U-tube This inverted tube filled with a solution in between the two. How we make our battery is we'll use little alligator clips to clip both metals, and then in the middle, we'll be able to have something either read how much voltage is given off, or we could actually power something if we wanted to. So again, it looks kind of weird, but this is how we make our batteries. We will go over this picture a little bit more. What I want to do on my next slide is just to go over the parts that make this up. So I'll flip back and forth as I do this. First off, a battery cell will have electrodes. Those are the metal poles. So we're going to have strips of metal in solution. Those are the electrodes. So again, I'll give you a second to jot this down. I'll flip back to the previous slide and I'll point those out again on that picture. I'm going to go back for a second. I'll come back to this if you didn't get this down. This is an electrode right here for copper. That's the copper metal pole. This is an electrode right here, zinc metal pole. Electrolyte is the solution that they are sitting in. That chemical will react with the metal pole. Perhaps you've heard the term electrolyte before, like with Gatorade commercials. Again, after exercising, you need to replenish your electrolytes. An electrolyte solution is typically just an ionic solution. Ionic solutions can help with that conduction of electricity as well, but they're going to be reacting in this case. Again, I'm going to go back to the previous slide and point that out and come back to this for those of you who didn't finish writing it all. But this copper solution right here is an electrolyte. Same for the zinc ion solution right here would be the electrolyte. So I have zinc metal sitting in its own ionic solution. I have copper metal sitting in its own ionic solution. Finally, that U tube is referred to as a salt bridge. Now remember, in chemistry, a salt is any ionic compound. We need that salt bridge to allow cations and anions to move about. Although I do mention on my very last bullet point, some batteries that you buy at like Walgreens don't even have that, because instead of two separate compartments, it's all just one big mixture instead. But what we'll be doing, we will have to include that salt bridge, that U-tube. And I'll give you a chance to jot that down. I'll go back to that slide. To show you again what I'm referring to. And I'm not too concerned about this last bullet point, because we will need a salt bridge with the setup that we are going to be doing. So if I go back to our picture again, the salt bridge is this tube right here. It's a glass tube, looks like a shape of a U, that's why it's called a U-tube, and we put a solution inside of it. That solution inside of it is going to allow some of the ions from here to flow in this direction, or ions here to flow in that direction. So it's connecting the two chambers. I connect the two metals with a wire. I connect the two solutions with the U-tube. So that's our salt bridge, it's referred to as. There are two different types of electrodes. One is a cathode. The cathode is the positive electrode. I think more important is what I have on this slide. The positive electrode is where electrons are attracted to. Just like a cation is a positive ion, a cathode is the positive electrode. Those of you who ever had to jump start a car battery, it's the red part of the car battery. It usually has a red cap on it. If it's a positive electrode, it should make sense that negative electrons are attracted to it. Now this is important because that picture that I showed you on the previous slide, at some point you're going to be able to label which end is the cathode, which end is the anode. So what part is gaining electrons, what part is losing electrons? That's something that we should be able to do. The cathode is the site of reduction. Because the cathode is where electrons are being gained, and reduction is to gain electrons. Remember, Leo goes Gur. Gur is gain electrons reduced. The cathode end of that battery cell would be the site of reduction. Last unit, I introduced two vocabulary terms of oxidizing agent and reducing agent. I introduced them then because in electrochemistry, those terms are used. The site of reduction is where the best oxidizing agent would be. Remember, an oxidizing agent is something that will be reduced. The other electrode is the anode. This is the negative end. This is the end that electrons are lost, which would make it the site of oxidation. Lose electrons oxidized. Now, typically, if we had more time, what I would do is my next slide goes over some general batteries. That's not that important to do, but there's an animation from the old chem textbook that I show. Instead, to wrap up this, once you get this jotted down, I want to go back to the previous slides to kind of show you this labeling. Again, today is just an introduction into it. Next class is all about electrochemistry. Again, the PES Pogo packet took a little bit longer than anticipated. But if I go backwards here, I started with this reaction. Zinc loses electrons to copper. If zinc loses electrons, it was oxidized. Are we okay with that statement? Copper gains electrons, it's reduced. So if I look at my picture, here's my copper strip right here. If copper is reduced, it is the cathode. So if I were to label it, this compartment right here is the cathode compartment. Zinc was oxidized. If you're oxidized, you're the anode compartment right here. So labeling this is part of what we will have to do. Again, there's more that we're going to do with it, but that's part of it. Last thing I want to bring up then to finish up notes to hopefully help you remember, cathode is where reduction occurs, anode is where oxidation occurs. Both cathode and reduction start with a consonant. Anode and oxidation both start with a vowel. That's probably the easiest way to remember the identification part that we will eventually have to do.